Part 1. The Ghost in the Machine. In the 1950s, punch cards were a common tool for storing and processing data. They enabled the categorization of information through physical holes punched in cards, representing specific data points or attributes. They facilitated the systematic classification and organization of data, allowing for efficient data retrieval and analysis in early computing systems. The systems often followed predefined hierarchies and structures, reflecting human-designed categorization schemes embedded into computer operations. In the modern era, metadata has emerged as a way to categorize and describe digital content. Metadata includes tags, labels, and descriptors that provide contextual information about data, facilitating searchability and organization. Metadata allows for dynamic and flexible categorization, enabling users to assign multiple tags to content based on various criteria, enhancing the granularity and specificity of classifications. Modern metadata systems often incorporate user-generated taxonomies and folksonomies, reflecting diverse perspectives and preferences in categorizing information, thus deviating from rigid predefined structures. Both punch cards and metadata systems rely on human interpretation and decision-making to assign meaning and context to data. The continuous involvement of human agency underscores the fundamental role of categorization in processing information effectively. The transition from punch cards to metadata marks an evolution in response to technological advancements and the digital transformation of information storage and retrieval processes. While the old systems were rigid and limited in scope, modern metadata frameworks offer greater flexibility, complexity, and customization, allowing for more nuanced and diverse categorization approaches. The shift to modern metadata has significantly enhanced the efficiency and scalability of data categorization processes, enabling rapid search and retrieval across vast datasets. Metadata systems provide opportunities for personalized categorization and contextual understanding, reflecting individual preferences, contexts, and interpretations. Modern metadata systems have democratized access to information, empowering users to navigate and interact with data in more intuitive and personalized ways. The human-driven nature of categorization in both punch cards and metadata systems raises concerns about potential biases, inaccuracies, and manipulation in how data is classified and interpreted. The transition from 1950s punch cards to modern metadata represents a continuum of human categorization processes in response to technological innovation and evolving information needs. While the tools and methods have evolved, the underlying principles of human interpretation, organization, and context-driven categorization remain constant. Understanding this continuity helps illuminate the ways in which human cognition and technology intersect in shaping how we categorize, interact with, and derive meaning from data in a digital age. In the era of early mainframe computers, batch processing was a prevalent method for handling large volumes of data. Programs were executed in batches, with data processed sequentially without the need for direct user intervention. Batch processing relied on standardized data formats and structures to ensure compatibility and efficiency in data processing tasks. Data points were organized into fixed formats to facilitate automated processing and analysis. As citizen information was input into mainframe systems for processing, it became standardized to fit the data structures required by batch processing programs. Personal details, such as names, addresses, and demographic information, were reduced to standardized data points with predefined fields and formats. The emphasis on uniformity and efficiency in batch processing led to the depersonalization of citizen data, treating individuals as data points within a system rather than unique individuals with distinct characteristics, experiences, and identities. Viewing citizens as standardized data points through batch processing set a precedent for uniform treatment based on data-driven categorizations rather than nuanced individual considerations. Standardized data points limited the context and richness of citizen records, potentially overlooking unique circumstances, needs, and complexities that could influence policy decisions and service provision. Batch processing enabled government agencies and organizations to streamline operations, automate repetitive tasks, and manage data more efficiently. However, This emphasis on efficiency sometimes came at the expense of personalized, human-centric approaches to citizen engagement. We had become a name and number inside a pigeonhole within an unfeeling machine. The legacy of viewing citizens as standardized data points in early mainframe batch processing has influenced the shift towards data-driven governance models. Decision-making processes increasingly rely on data analytics, metrics, and standardized indicators to inform policy formulation and program evaluation. The reliance on standardized data points for citizen management highlights the importance of privacy protection, data security, and ethical considerations in processing and storing sensitive personal information. Safeguarding individual privacy rights becomes paramount in data-centric governance frameworks. IBM's early systems, including mainframes and punch-card technologies, relied on rigid, standardized data structures for processing information efficiently. Data was organized into fixed formats, imposing a strict logic on how information was input, stored, and analyzed. These early systems were characterized by centralized control and hierarchical structures, reflecting a top-down approach to data management and system architecture. Decisions were made based on predetermined rules and logic embedded within the technology. In modern database surveillance systems, vast amounts of data are aggregated from diverse sources and processed using sophisticated algorithms. Individuals are categorized, profiled, and monitored based on their digital footprints, creating comprehensive profiles that go beyond standardized data points to include behavioral patterns, preferences, and interactions. Contemporary surveillance architectures rely on algorithms and machine learning models to analyze data, make predictions, and automate decision-making processes. The rigidity of logic in these systems is manifested through predetermined algorithms that determine how data is processed, interpreted, and acted upon. The centralized control and standardized data structures seen in IBM's early systems have evolved into centralized surveillance architectures that exert control over vast troves of data. The foundational principles of hierarchical data management persist in contemporary surveillance frameworks, albeit on a more extensive and complex scale. While the rigid logic of early systems limited the scope of data processing and analysis, contemporary surveillance systems leverage advanced technologies to extract insights, correlations, and patterns from massive datasets. The rigidity of logic is now embedded in sophisticated algorithms that power surveillance operations at scale. The shift from rigid logic in early IBM systems to contemporary database surveillance raises significant privacy and ethical concerns. The detailed profiling and monitoring of individuals through surveillance architectures challenge notions of autonomy, consent, and individual freedoms, sparking debates on data privacy, surveillance oversight, and ethical governance. Notice that if the platforms you give your data to are hacked, there is no comeback on the actual platform. They just carry on as normal, while your data circulates on the dark web, sold to the highest bidder. The foundational architecture of contemporary database surveillance consolidates power within entities that control and manipulate vast amounts of data, influencing societal dynamics, governance structures, and individual freedoms. The surveillance infrastructure built on the rigid logic of data processing poses threats to privacy, autonomy, and civil liberties, prompting calls for transparency, accountability, and regulatory safeguards to protect individuals from unwarranted intrusions. Part 2. The efficiency trap. Historically, corporate inventory management involved manual record-keeping systems to track goods, materials, and supplies. Businesses maintained records of stock levels, transactions, and supply chain operations using paper-based or rudimentary digital systems. Companies sought to optimize inventory levels, reduce stockouts, and streamline procurement processes to enhance operational efficiency and cost-effectiveness. With the advent of databases and digital technologies, corporate inventory management evolved to include automated data storage, retrieval, and analysis. Companies began to centralize inventory data, enabling faster access to real-time information for decision-making. Advanced data analytics tools were utilized to forecast demand, optimize inventory levels, and improve supply chain efficiency based on historical sales data and market trends. Tech giants began accumulating vast amounts of data on user behaviors, interactions, preferences, and habits through their platforms and services. This data included browsing history, purchases, social media activity, and more. By leveraging machine learning algorithms and artificial intelligence, tech companies started to analyze this data to develop predictive behavioral models. These models forecast user preferences, behaviors, and actions to personalize content, target advertisements, and optimize user experiences. The transition from corporate inventory management to predictive modeling by tech giants involved a gradual accumulation of data from inventory records to user behaviors and interactions. As data sources expanded and became more granular, predictive modeling capabilities evolved to capture nuanced user patterns and trends. Tech giants employ sophisticated data analysis techniques to extract meaningful insights from vast datasets, enabling them to predict user behaviors with precision and accuracy. Insights derived from predictive modeling inform targeted marketing strategies, content personalization, and product recommendations. The shift from traditional inventory management to predictive behavioral modeling represents a move towards personalized user experiences, tailored recommendations, and targeted interventions based on anticipated user actions and preferences. The proliferation of predictive behavioral modeling raises significant privacy concerns regarding data collection, user profiling, and targeted advertising. Users may feel their privacy is compromised when tech companies leverage personal data to predict and influence their behaviors. Ethical considerations surrounding consent, transparency, and data usage come into play as tech giants harness predictive modeling to influence user decisions and actions. In the 1960s, there was a growing emphasis on administrative efficiency and data processing in various sectors. Government agencies, corporations, and organizations sought to streamline operations, reduce paperwork, and centralize data for improved decision-making. Advancements in computer technologies led to the integration of early mainframe systems for processing large volumes of data. This shift towards computational efficiency laid the groundwork for more centralized and automated administrative practices. The pursuit of administrative optimization through digital technologies contributed to the creation of centralized data repositories containing vast amounts of personal information. Individuals' details, such as demographics, financial transactions, and interactions, were captured, stored, and linked within these systems. As administrative processes became increasingly digital and interconnected, disparate data points from various sources were aggregated into comprehensive digital dossiers without individuals' explicit consent or awareness. This unintentional data aggregation laid the foundation for the creation of involuntary digital profiles. The formation of involuntary digital dossiers raised significant privacy concerns, as individuals' personal information was collected and stored without their knowledge or consent. The lack of transparency and oversight in data collection practices exacerbated privacy vulnerabilities, exposing individuals to potential misuse or exploitation of their data. Centralized repositories of personal data created security vulnerabilities, as the concentration of sensitive information within digital systems increased the risk of data breaches, unauthorized access, and misuse. The unintentional creation of digital dossiers heightened concerns about data security and protection. The unintentional creation of digital dossiers marked the early stages of surveillance practices, wherein individuals' activities, behaviors, and interactions were monitored and recorded without their direct consent or awareness. This laid the groundwork for the expansion of surveillance mechanisms and data collection practices in later years. The aggregation of individual data points within involuntary digital dossiers facilitated the development of behavioral profiling techniques, enabling organizations to predict and influence individuals' behaviors, preferences, and decisions based on comprehensive digital profiles. This evolution towards predictive modeling and targeted interventions stemmed from the initial aggregation of data for administrative optimization purposes. The creation of involuntary digital dossiers challenged individual autonomy and agency, as personal information was collected and utilized without individuals' explicit consent or control. This raised ethical concerns about the extent to which individuals should have sovereignty over their digital identities and data. The emergence of involuntary digital dossiers in the 1960s prompted discussions about data privacy, security, and governance, leading to the development of regulatory frameworks and laws aimed at protecting individuals' rights in the digital realm. The ethical considerations raised by the birth of involuntary digital dossiers continue to shape contemporary debates on data privacy and surveillance practices. In the early days of computing, the need for centralized mainframe control arose from the quest for efficiency in data processing. Mainframes facilitated large-scale data processing tasks, allowing organizations to centralize computational resources and manage data in a structured manner. Centralized mainframe control enabled standardized data management practices, ensuring data consistency, reliability, and accessibility across diverse applications and departments within an organization. The evolution from mainframes to cloud computing marked a shift towards decentralized computing resources. Cloud-based services offer scalability, flexibility, and on-demand access to computational resources, allowing organizations to offload infrastructure management and focus on core operations. In the era of cloud computing, algorithmic governance has emerged as a paradigm where automated algorithms and data-driven decision-making processes influence policy enforcement, resource allocation, and service provision. Cloud-based platforms leverage algorithms to optimize operations, streamline workflows, and enhance user experiences. Cloud-based algorithmic governance relies on vast amounts of data to inform decision-making processes in real time. Algorithms analyze data patterns, forecast trends, and optimize operations based on predefined rules and objectives, mirroring the logic of centralized mainframe control in a distributed computing environment. Algorithmic governance in the cloud era aims to personalize services, tailor recommendations, and optimize resource allocation using data-driven insights. This evolution builds upon the historical foundation of centralized control while leveraging cloud-based technologies to enhance scalability, accessibility, and efficiency in governance practices. Cloud-based algorithmic governance offers enhanced scalability compared to traditional mainframe systems, allowing organizations to adapt to changing demands and process vast amounts of data in real time. The centralized control inherent in cloud-based algorithmic governance raises concerns about data privacy, security, and transparency. Ensuring robust data protection measures and ethical governance frameworks becomes crucial in safeguarding individual rights and mitigating risks associated with algorithmic decision-making. The shift towards cloud-based algorithmic governance poses regulatory challenges related to data sovereignty, jurisdictional issues, and accountability in decision-making processes. Addressing these complexities requires a multidisciplinary approach that balances technological advancements with ethical considerations and regulatory compliance. Part 3. Architecture of invisibility. In the past, bulky physical mainframes characterized computing infrastructure, requiring dedicated space, cooling systems, and maintenance. These centralized machines processed data and managed operations for organizations, albeit with limited flexibility and scalability. Advancements in technology led to a transition from centralized mainframes to distributed computing systems, where processing power and storage were distributed across networks, allowing for greater flexibility, redundancy, and scalability. In the prescient, technological innovations have facilitated the miniaturization and integration of sensors into urban infrastructure. These invisible sensors, embedded in various devices and structures, collect real-time data on environmental conditions, traffic patterns, energy usage, and more. The deployment of Internet of Things devices and smart city initiatives leverage these sensors to monitor and manage urban environments efficiently. Seamless integration of sensors enhances data collection, analysis, and decision-making to optimize resource utilization and enhance quality of life in cities. Invisible sensors embedded in urban infrastructure enable data-driven decision-making processes that inform city planning, traffic management, energy efficiency, waste management, and public services. Real-time data insights empower city officials to respond proactively to challenges and enhance urban resilience. The integration of invisible sensors enhances the delivery of services and utilities in cities, promoting efficiency, sustainability, and responsiveness to citizen needs. From smart parking systems to adaptive lighting and waste management, sensor-enabled infrastructure optimizes operations and enhances urban living experiences. Invisible sensors in urban infrastructure improve connectivity and communication between systems, devices, and stakeholders, fostering a more interconnected and responsive city ecosystem. The proliferation of sensors raises privacy and security concerns related to data collection, storage, and usage. Safeguarding sensitive information while harnessing the benefits of sensor technology requires robust data protection measures and ethical data governance frameworks. Sensor-enabled urban infrastructure plays a crucial role in promoting environmental sustainability by monitoring energy consumption, reducing emissions, optimizing resource usage, and mitigating the impact of urbanization on ecosystems. In the early days of computer programming, the focus was on developing stable, reliable systems that could process tasks efficiently. Programmers adhered to structured, logic-based approaches to code development to ensure system functionality and performance. The cold logic of early programming prioritized system stability and operational reliability over individual factors such as privacy rights. Programmers worked to minimize errors, optimize processes, and maintain consistent system operations, often at the expense of considering privacy implications. Early programming emphasized data processing and management to ensure accurate and reliable information handling within computer systems. Privacy concerns were often overlooked in favor of optimizing data structures and access methods for efficient processing. Programmers focused on implementing robust security measures and error-checking mechanisms to protect system integrity and prevent unauthorized access. While this prioritized system stability, it sometimes disregarded the privacy rights of individuals whose data was processed within the system. Early programming practices tended to prioritize functional requirements, performance optimization, and error handling procedures over explicit privacy considerations. This lack of emphasis on privacy led to the inadvertent collection, processing, and storage of personal data without robust privacy safeguards. The cold logic of early programming was system-centric, focusing on operational efficiency and stability at the system level rather than individual user privacy concerns. Privacy rights were often compromised in favor of system performance and reliability. The cold logic approach to early programming limited the incorporation of comprehensive data protection measures to safeguard individual privacy rights. Minimal attention was given to data anonymization, encryption, and access controls to protect sensitive information. Early programming practices often lacked transparency regarding data processing activities, making it challenging for individuals to understand how their personal information was being collected, stored, and used within computer systems. The prioritization of system stability over individual privacy rights in early programming raises ethical considerations regarding data handling practices, consent mechanisms, and transparency requirements to respect and uphold privacy rights within digital environments. Contemporary programming paradigms emphasize privacy by design, integrating privacy considerations into the development lifecycle of software systems to uphold individual rights and data protection principles. The evolution towards privacy-first programming aligns with regulatory requirements such as the General Data Protection Regulation and other privacy laws that mandate organizations to prioritize individual privacy rights in data processing activities. Modern programming practices recognize the ethical responsibility of developers to prioritize individual privacy rights, implement privacy-enhancing technologies, and promote transparency and accountability in data processing practices to protect user data effectively. In the old days, bureaucratic systems were characterized by intricate processes, paperwork, and hierarchical structures that required explicit human involvement and decision-making at various levels. Communication was often formal, time-consuming, and dependent on manual interactions. Bureaucracies of the past operated with a degree of transparency, as decision-making processes were visible, documented, and determined by organizational regulations and guidelines. individuals had a sense of oversight and accountability within the bureaucratic framework. Whereas, in modern smart cities, data harvesting is often silent and autonomous, facilitated by interconnected sensors, IoT devices, and data collection mechanisms embedded in urban infrastructure. Data is gathered in real time without overt human intervention, enabling the automated monitoring of various urban metrics. Smart city systems leverage algorithms to process vast amounts of data, derive insights, and automate decision-making processes in areas such as traffic management, energy efficiency, waste disposal, and public services. This autonomous data processing enables cities to respond swiftly to dynamic urban challenges. Bureaucratic systems were visible and audible, with a clear structure of decision-making processes, channels of communication, and accountability mechanisms. But autonomous data harvesting operates silently and inconspicuously, with data collection processes embedded within the urban environment, often without direct human awareness or interaction. Human involvement was central to bureaucratic operations, with manual interactions, approvals, and oversight required at different stages of decision-making processes. But autonomous data harvesting minimizes direct human involvement in data collection and processing, relying on technologies to gather, analyze, and act on data in real time without explicit human intervention. Privacy controls were often explicit within bureaucratic systems, with regulations and protocols dictating data handling practices to ensure transparency and protect individual rights. But autonomous data harvesting raises privacy concerns, as data is collected passively and continuously, potentially leading to challenges in data ownership, consent, and control over personal information in the digital urban landscape. The landscape is shifting beneath our feet, and the coming generations will accept this as normal. Because they never knew anything different, the past will be as sanitized as a kitchen work surface. Part 4. The digital mirror. Early data sorting techniques emerged as essential methods to organize, categorize, and analyze information within computational systems. Sorting algorithms such as bubble sort, merge sort, and quick sort were used to arrange data in a structured manner for efficient processing. It involved manual categorization or rule-based systems where information was classified based on predetermined criteria or data attributes. These techniques laid the groundwork for more advanced data processing methodologies and algorithms. Advancements in data analytics and machine learning algorithms have led to the development of feedback loops in digital environments. Feedback loops enable systems to gather data, analyze patterns, and adjust behaviors based on observed outcomes, creating self-reinforcing cycles of data-driven decision-making. Feedback loops leverage data from user interactions, preferences, and behaviors to personalize content, tailor recommendations, and predict future actions. In social and political contexts, these loops shape user experiences, influence opinions, and drive engagement through targeted messaging and content delivery. Feedback loops in social media platforms and online environments amplify echo chambers, where individuals are exposed to information that aligns with their existing beliefs and preferences. This reinforcement can lead to polarization, information bubbles, and the spread of misinformation that shapes social and political discourse. They are powered by machine learning algorithms, may inadvertently perpetuate biases, propagate false narratives, or amplify certain voices over others, impacting perceptions, decision-making processes, and public discourse in social and political contexts. In social and political settings can influence user behavior, it can shape opinions, and drive engagement through targeted messaging, personalized content, and algorithmic recommendations that cater to individual preferences and tendencies. The loops reshape the information ecosystem by filtering content, amplifying certain narratives, and influencing user interactions in digital spaces, impacting societal perceptions and collective understandings of social and political issues. Addressing the impact of feedback loops on social and political realities raises regulatory challenges related to data privacy, algorithmic transparency, content moderation, and accountability in digital platforms to mitigate potential harms and safeguard democratic principles. Understanding the dynamics of feedback loops empowers citizens to critically engage with information and question algorithmic influences, and advocate for ethical data practices, transparency, and accountability in shaping social and political discourses. The Internet's ability to retain records of past actions, mistakes, and nonconformities creates a sense of a permanent digital footprint that individuals carry throughout their lives. Past errors or nonconformities may resurface, influencing perceptions and engagements within online and offline contexts. The proliferation of social media and online platforms magnifies the impact of errors or nonconformities, as information can quickly spread, become viral, and be subject to scrutiny or judgment by a global audience. Living within a system that remembers every mistake or nonconformity can lead to persistent anxiety, stress, and fear of judgment. Individuals may feel a constant pressure to maintain a flawless online image, leading to authenticity concerns, self-censorship, and heightened emotional distress. The perpetual record of errors may impact individuals' self-perception, self-esteem, and identity formation processes. Past mistakes or nonconformities may shape how individuals view themselves and how they believe others perceive them, influencing emotional well-being and mental health. Fear of being judged based on past errors or nonconformities may result in social stigma, ostracization, or isolation. Individuals may experience feelings of shame, embarrassment, or insecurity, affecting their willingness to engage with others and participate in social interactions. The need for constant vigilance in managing one's online presence and reputation due to the lingering memory of errors or nonconformities can be mentally taxing and time-consuming. Individuals may dedicate significant efforts to curating a specific online persona to mitigate potential repercussions from past actions. The psychological burden of past mistakes remembered by the digital environment can strain interpersonal relationships, causing trust issues, communication barriers, and challenges in building authentic connections. The fear of judgment or exposure may hinder vulnerability and openness in human interactions. Encountering a system that remembers every error or nonconformity can test individuals' self-worth and resilience, requiring coping mechanisms, self-compassion, and psychological fortitude to navigate the complexities of living in a digitally archived world. Building digital literacy skills and empowering individuals to understand data privacy, online reputation management, and responsible digital citizenship can help mitigate the psychological impact of a constantly remembered online presence. Cultivating forgiveness, a growth mindset, and self-compassion can aid individuals in reframing past mistakes as opportunities for learning, growth, and personal development, rather than sources of perpetual shame or anxiety. Part 5. Breaking the logic. In this envisioned future, algorithms and AI systems are designed to be transparent and explainable, enabling users to understand how decisions are made and the rationale behind outcomes. Explainable AI techniques such as interpretable models, feature importance analysis, and decision tree visualization enhance transparency and accountability in algorithmic processes. Implementing regular algorithmic audits and assessments to evaluate the fairness, bias, and ethical implications of AI systems ensures transparency and compliance with established guidelines, regulations, and societal values. Organizations prioritize data transparency by clearly communicating data collection practices, usage policies, and sharing protocols to empower individuals with knowledge and control over their personal information. Transparent data governance frameworks foster trust, accountability, and ethical data handling practices. Adaptation of privacy by design principles ensures that privacy protections are embedded into systems from the outset, promoting transparency, user consent, data minimization, and privacy-enhancing technologies to safeguard individual rights and mitigate risks of data misuse. Establishing ethical guidelines, standards, and frameworks that govern the development, deployment, and use of AI systems promotes transparency, accountability, and responsible innovation in aligning technology with societal values, human rights, and ethical principles. Implementing robust governance mechanisms, oversight bodies, and regulatory frameworks ensures accountability, transparency, and compliance with ethical standards, empowering stakeholders to monitor, evaluate, and address potential risks associated with AI technologies. embracing a future where transparency replaces the opaque black box. Logic inherited from the mainframe era offers a transformative vision of responsible, ethical, and human-centric technology development. By prioritizing transparency in algorithms, data governance, and ethical AI practices, organizations can build trust, foster accountability, and empower individuals with greater control over digital systems and their societal impacts. Investing in transparent technologies, ethical frameworks, and governance mechanisms paves the way for a more equitable, inclusive, and sustainable digital future, where technology serves as a driver of positive change, innovation, and societal advancement through transparency-driven decision-making and ethical AI practices.